container. So this is under pressure. Now, sometimes when I'm using this and I'm getting ready to go out and I desperately need some, like I said, I'm not sure why I would need some, but I desperately need some and there's hardly any left, I find myself shaking it and trying to get the last little bit out, and then something amazing happens. Here I got the last little bit out of this pressurized can and the can gets cold. And then I get excited. Here I am getting nervous about my roots showing, but in the meantime, I'm getting excited about the science because the can gets cold. And today I'm going to explain to you why the can gets cold when I get the last bit of gas out of here or pressure out of here.
Hey, Chem Jen.
Yeah.
I like your shirt.
Thank you. All of my money goes there, so decided I'd represent. So why does my can get cold when I get rid of all of the pressure in the can? In other words, when I decrease the pressure in my can, why does the temperature of my can go down? And conversely, if I increase the pressure on something, should the temperature go up? Well, let's first of all talk about this based on the kinetic theory. And for that, we're going to pull in our PhET video again. Here we are back on our phet.colorado.edu page, and you notice I've got the volume on constant, and I'm going to pump some gas into here. And I'm keeping my volume constant. Now I've got a lot of gas in there, and I want you to notice that the pressure is increasing as I pumped more and more gas in there. Also notice my temperature. I can decrease the pressure in two ways. I can decrease the pressure by either removing some gas or by cooling it down. Let's start by cooling it down. Watch what happens when I cool it down. I decrease the pressure. Watch what happens when I heat it up. I increase the pressure. So I can increase and decrease pressure by altering the temperature. I can also, however, increase pressure by just simply adding more gas. There I've increased the pressure by adding more gas. So if I let some gas out, I'm decreasing the pressure. And this is Gay-Lussac's law. Gay-Lussac's law says that pressure and temperature are directly related. That means as one goes up, the other goes up, and as one goes down, the other goes down. Now I told you that when I empty my bottle, my root concealer, and it gets really, really cold, it's because there's not as many molecules colliding with the sides of the container, and thus the temperature is going to go down. Now remember, we talked about how temperature is directly related to kinetic energy. So the less pressure I have, the less collisions I have, the slower the molecules are moving, and thus the lower the kinetic energy and the lower the temperature. This is Gay-Lussac's law. Gay-Lussac's law says that pressure over temperature for a given system will give you a constant, or P1 over T1 equals P2 over T2. So this is our third law. We've learned Boyle's law, Charles' law, and Gay-Lussac's law, and now let's apply it to a math problem. It says right here the pressure on your car's tires is 30 psi. So this is pressure at 28 degrees Celsius. There's a temperature. So this pressure and this temperature goes together. So we have P1 equals 30 psi, T1 equals 28 degrees Celsius, and ding, 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 we don't want Celsius. So remember, we're going to add 273 to convert to Kelvin. And you go on a long road trip on a hot summer's day. You notice that going over bumps on the road is really jerking you around. So you stop and remeasure the pressure in your tires. To your astonishment, it measures 38 psi. So this is our second pressure reading. What temperature are your tires in order for the pressure to be this high? So now we're going to solve for T2. Our formula for Gay-Lussac's law is P1 over T1 equals P2 over T2. It's a direct relationship, so we have to divide the quantities. In Boyle's law, it was inverse, so we had to multiply the quantities. So I have 30 over 301 equals 38 over x. Now, some people get a little bit uncomfortable when x is in the denominator, but math is math, and you get to cross multiply across the equal sign right here. So don't let that x in the denominator frighten you. Okay, so now we have 30x equals 38 times 301, 11438. And now we want to isolate the x, so we're going to divide both sides by 30. And when we do that, we get x equal to 381. And I'm only allowed 2 sig figs, so this is going to be 3.8 times 10 to the 2. What is this? What did I just solve for? Oh, I solved for a temperature, and my temperature is in Kelvin, so this is going to be 3.8 times 10 to the 2 Kelvin, or you could also write it as 380 Kelvin. If you don't put the period there, it can stand for 2 sig figs. Now, 380 Kelvin may not have much context for you, so I'm going to go ahead and subtract out 273 and get it back into Celsius. And my tires are 107 degrees Celsius. Well, we know that water boils at 100 degrees Celsius, so my next question is, are my tires in danger of melting? Well, if my tires were water, they would be boiling, but obviously my tires are not water. So I looked up the melting temperature of a rubber tire, and it's 600 degrees Celsius. Actually, that value changes depending on where you look. But anyway, it's way higher than 100 degrees Celsius, because otherwise we wouldn't be able to drive cars on rubber tires in Florida. Okay, so our car tires are safe, and I may have to release a little bit of pressure. Now, my car has a lovely digital pressure gauge, and being a science person, I like to just put it on that setting, and then at the end of my drive, look and see how much it's increased on a hot day here in Florida. Now, in the heat, you would have to have slightly less pressure in your tires. If you lived up north, like in Minnesota or somewhere, you would have to have slightly more pressure in your tires. Why? All because of our friend Gay-Lussac and Gay-Lussac's law.